Okay, so what I want to do today is I want to talk about Plancherel's formula. And someone was just telling me recently that they saw this arising on a, was it a general exam or qualifier exam in grad school? Was it you, Craig?
Yeah, like qualifying.
Okay, so in a qualifying exam in graduate school. So Plancherel's formula. Let's let f be nice. Then the sum, n goes from minus infinity to infinity, of f hat of n squared is the integral from 0 to 1 of f of x squared dx. That's that one. So the question is, what is nice? And if you take an analysis class, you will rigorously define what is nice. Can anybody give me an example of a nice function? Continuous. Continuous, and thank you for not saying identity 0. And now that continuous has been said, since the identically 0 function is continuous, you may not say the identically 0 function or any constant function and receive credit. Oh, I know.
Who said that? Who said continuous?
So, can anybody give me another example of a nice function? Yes.
Uniformly continuous?
It will, in fact, anything continuous would be uniformly continuous.
Finitely many discontinuities.
Finitely many discontinuities. If you look at the statement, however, it really suggests what the definition of nice should be.
Should be differentiable.
If differentiable would definitely be nice, but almost every function is differentiable nowhere. So imposing differentiability is helpful for proofs, but not helpful for the most general statement. So if you look at the statement, it's screaming at you. I'm sorry?
It's an L.
Yes. The sum of the squares of the Fourier coefficients is equal to the L2 norm, the integral of f squared. If the integral of f squared is infinite, things could break down. I really want this integral to be finite. Okay, so this statement strongly suggests what functions we should study. How many of you have taken measure theory? So have you seen going from L1 functions to step functions to continuous functions? Have you seen that those arguments? Okay. So what I'll do is I want to talk just a little bit about some of the analysis tools needed. When I do the proof, I would really like to just work with a function that's continuous and prove the result for continuous functions, and then say, well, if I can do it for continuous functions, I can really do it for any function I need to study. Because you give me any function, and I can find in some sense a continuous function which is arbitrarily close to it. Okay, so this is one of the big ideas in analysis, is rather than working with the function you're given, work with the functions that have nice properties. And in fact, later we'll look at the Schwartz functions. Not only are they continuous, but they're infinitely differentiable, and they have great decay properties. Alright, so maybe what I'll do is I'll first prove Plancherel's formula if f is continuous, and then talk about how would you generalize this. Okay, so the first step is Bessel's inequality. And it says, if f is in L2, then the sum of f hat of n squared is less than or equal to the integral from 0 to 1 of f of x squared dx. So then what's the rest of the lecture going to be devoted to? I'm sorry? Well, no, but Bessel's inequality is that it's, this is less. Oh, I see what you're saying. Sure, then if you just prove the other way, that's greater than equal to. But unfortunately, the only way we can prove that it's greater than equal to is to prove that it's equal. So, right, so the rest of the lecture just becomes, is Bessel's inequality an equality? And so here's the proof. Consider f minus Sn of f dotted with f minus Sn of f. What can you tell me about the dot product? So what do I know about the dot product?
It's distributed.
It's distributive. What else? What do you know about that value?
That's just the magnitude squared of f minus Sn of f.
Okay, good. It's the magnitude squared, and that is
Length
the length, and that is
greater than 0. If it's
almost.
not 0.
Almost. So greater than or equal to 0. Right. That's the key observation. I'm taking the length of something. The length of something is greater than or equal to 0. How many of you have seen a proof of the Cauchy-Schwarz inequality? Okay, if you haven't, go home tonight, see a proof of Cauchy-Schwarz. Okay? This is another way of starting your proof of Cauchy-Schwarz, is this idea that length is non-negative. A lot of people call this the most useful inequality in mathematics. It's essentially saying, if x is real, x squared is greater than or equal to 0. This is considered, in many people, the #1 inequality of all time. It's amazing how powerful this is. Right? Let's see what we get. We get 0 is less than or equal to, if I expand, I get f dotted with f minus Sn f dotted with f minus f dotted with Sn of f plus Sn of f Sn of f. Okay, I'm not going to go through all the steps. I just want to do enough so that you can get a sense of what's going on. So I get 0 is less than or equal to f dotted with f minus, turns out these are all going to be the same. And so I'm not going to go through all the details of the calculation. You get Sn of f, Sn of f. So again, you can just do the calculation. So I get Sn of f dotted with Sn of f is less than or equal to f dotted with f. But when you look at what is Sn of f dotted with Sn of f, Sn f dotted with Sn of f is going to be the integral from 0 to 1, the sum, n goes from minus n to n, f hat of n, en of x, times the sum, m goes from minus n to n, f hat of m, e, the m of negative x, dx. When I integrate the en and the em, the only time the integral is not 0 is when n equals m. So this then just becomes the sum, n goes from minus n to n. Oh, and I'm sorry. I have to take the complex conjugate. Right? When I do the inner product, it's the complex conjugate. The complex conjugate of the exponential term is just replacing x with negative x. But here, I have to remember to put a bar over the Fourier coefficient. So I get f hat of n, f hat bar of n. Oh, well, that's just the length of f hat of n squared. So this is just the sum, n goes from minus n to n, of f hat of n squared is less than or equal to the integral from 0 to 1 of f of x squared dx. Because just the dot product of f with itself is just the integral of magnitude f squared. So again, you can just do the algebra for all of these three things. You'll see all of these things are the same. By using complex conjugates, this is just going to become the sum of f hat of n squared. So this tells us a lot of things. What can we deduce from this statement? Can we deduce Bessel's inequality from this statement? So, being explicit, Bessel is minus infinity to infinity. Can we get that from this? Yeah. This holds for any n, so if we take the limit as n goes to infinity, we're okay. So all we have to do is just take the limit as n tends to infinity. And if we take the limit as n goes to infinity, we've got Bessel. Okay, what else have we deduced? I claim that this gives you some information on the Fourier coefficients of f. What can you deduce about the Fourier coefficients of f? So imagine f is in L2 so that this sum is finite, so that this integral is finite. What can you now deduce about f hat of n?
It's going to 0.
It's going to 0. So if I give you a function in L2, its Fourier coefficients have to decay. So that fact is worth isolating. And so versions of this are called the Riemann-Lebesgue lemma. I like the name of this lemma because it, basically honors the two different people whose types of integrals we consider, one happy lemma now for the two of them. What we've shown is f in L2 implies the limit as n goes to infinity, or I guess we could do plus or minus infinity, of f hat of n is 0. So the question is, how much more is true? And so it turns out, if your function is differentiable, you can get decay rates. So if f is k times differentiable, I think you get f hat of n divided by n to the k tends to 0. So the more differentiable the function is, the better bounds you have on how quickly it tends to 0. Another thing is, it's still true if f is just an L1. Unfortunately, the proof we use doesn't work. Why does the proof we just used not work if f is just an L1? So why does Bessel's inequality not imply the Riemann-Lebesgue lemma if our function is just L1? So our argument was, we used if f is L2, that the sum of f hat of n squared was less than or equal to the integral from 0 to 1 of f squared dx. Why doesn't this still imply the result if f is just L1?
Because maybe it's an order of magnitude smaller, could diverge. Right?
You're close. So if my function is an L2, is it an L1?
Not necessarily.
Not necessarily, right? Danger. Take for instance, f of x is x to the negative 3/4. That function is an L1, but it's not an L2. So if I just tell you the function is an L1, this integral could be infinite. Wow, I know the sum of non-negative numbers is at most positive infinity. That's got to be worth, right? I got to be able to deduce things from that, right? Okay, there's no chance of making any deductions from the fact that a sum of non-negative items is at most positive infinity. So this inequality is completely useless if I just give you an L1 function. If the function happens to be L2, okay, now more is true. So then the question becomes, how would you prove this for an L1 function? The idea is to try to approximate maybe an L1 function by an L2 function, so that maybe the difference in the integrals is not that bad. Okay? So this is a very important fact. If my function is an L2, then the Fourier coefficients are decaying. If my function is differentiable, they decay rapidly. Are continuous functions in L2? Or, to be more specific, are they in L2 of the interval 0, 1? So if I give you a continuous function on 0, 1, is it square integrable? Okay, so I see you nodding your head. Why is it square integrable?
Because it's bounded.
Yeah, it's bounded. Continuous function is bounded. Got to be a little bit careful if you take a measure theory class. It's not quite enough to say, a bounded function is integrable, because I could give you something really strange. I give you the characteristic function of the rationals, and that's not Riemann integrable. So really, you need a better notion of integration lurking behind all this. Okay, I'm not assuming you guys have seen measure theory. I just want to throw out a few comments because I know some of you have taken measure theory, and so you can see a little bit about what's going on. Okay, so this was step one of the proof of Plancherel. So we're beginning to see why Plancherel might be true. It's basically just saying that the Bessel inequality is an equality. So the question becomes how to finish the proof. So step two, and again, we're going to assume f is continuous. What do you know about a continuous function with respect to Fourier series?
It has decay.
It has decay. What else? So I'm giving you a very specific beeline path through Fourier analysis, stopping to prove just the results I need. What facts do we know about continuous functions and their Fourier series? Whose theorem did we prove? Fayet. So we have Fayet's theorem, that you give me a continuous function, I can uniformly approximate it by its weighted Fourier series. There were no votes, including myself, to prove Dirichlet's theorem that if your function is differentiable, then you can approximate it with a regular Fourier series. It's essentially the same proof, that's why even I didn't vote for it. But if my function is continuous, then I can just use the regular Dirichlet series. So the idea is, maybe I can somehow use the fact that I have a really good approximation of my function f with its Fayet series. And so I'm going to use the following notation. L2 squared means the integral of f of x squared dx. So this is the L2 norm. The subscript 2 here means I'm integrating f to the second power, and the square just means I'm squaring it. So really, the length of this should be the square root of that. So this is the square of the length. And so what I want to do is I want to approximate how far Bessel's inequality is from the truth. So I have f minus Sn of f. And the question is, as n gets very large, what do you think that goes to?
0.
That should go to 0. And so I'll do the proof using Fayet series. So I can write this as f minus Tn of f plus Tn of f minus Sn of f squared. So I've added 0, right, one of my favorite things to do. Now what should I do? Group. So I want to group the first two together and the second two together. And I claim this is less than or equal to 4 f minus Tn of f squared plus Tn of f minus Sn of f squared with a factor of 4. I have no idea what that is over there. So we rewrite. Oh, that's the t going into the line. Okay. So what I'm using is, if I have a plus b squared, that's at most 4a squared plus 4b squared. And you can assume no. So why is that true? So why would a plus b squared be at most 4a squared plus 4b squared?
A plus b squared is greatest when a is equal to b.
So it's greatest when a equals b. Imagine b is larger than a in absolute value. Then the best this could be is if a equals b, and I would have 2b, which squares to 4b squared. And if a was larger than b in absolute value, then the best I could have was b when b equals a. I would get, again, 2a squared. So 4 is not the best number I can use. I can use a smaller number than 4. Okay? I have already lost any chance of impressing you by having all of my proofs end up as epsilon. I think there was some disgust yesterday that we had this embarrassment of a 2b plus 1 times epsilon. Okay, no, there's no embarrassment.
Oh, we're good.
Oh, it's embarrassing. Okay. Oh, you're just shaking your head in disgust. I'm sorry. Okay, so I've already lost the class. It's already too late for me to salvage myself. I'm not going to even try to get the optimal number. The other thing is this really gives you an opportunity to see mathematicians at our best. We're lazy. We aim to be lazy, right? I don't need a better number here. Maybe if I care about how fast something is happening and I'm doing some computations, but right now I'm being a theoretician. And the other thing is, at the end of the day, I'm going to get an equality. I'm just trying to show that in the limit, as n gets very, very large, this term doesn't matter. Do I really care if it's a 4, a 5, or a 3? No. Don't spend time trying to find the best bound in this particular case. For other things, of course, try to come up with good answers. When you're trying to figure out how many people can this elevator take, that's a good one to get right. Okay? Over here, the 4, don't worry about is it 4, is it 3, is it 2. As a nice exercise, I urge you to try to figure out what is the smallest number you can put there and still have truth. Okay? What's the smallest number? But over here, 4 is absolutely fine. As n gets very, very large, what can I say about this? Where does this term go to? That goes to 0. So if I can show that this term goes to 0, we'll be in great shape. Okay?
Sorry, why did the first term go to 0 again?
Well, because f is continuous, and so by Fa's theorem, I can uniformly approximate f by the weighted Fourier series. So this is Fa's theorem. I think the accent is on the second E. I'll try that today. So if I can show that this term goes to 0, or at least its integral goes to 0, then the integral of this goes to 0. This was my error term from Bessel. And so if I can show that this goes to 0, then Bessel's inequality is an equality. So if this goes to 0, done. So because Bessel gave us the sum, n goes from minus n to n, f hat of n squared plus the L2 norm of f minus Sn of f squared equal the integral from 0 to 1 of f of x squared dx. So this presence was what prevented Bessel's inequality from being an equality. If I can show that this goes to 0, we win. So the question is, how do I want to analyze the L2 norm of f minus Sn of f? How do I want to analyze that integral? Well, I know that I can approximate f really well by its Fa series. And so what I'm going to do is I'm going to just add 0. This piece is now fine. I can make it as small as I want, so if I integrate this, it's still going to be small. And now I just have to show that the integral of this piece is small. All right, well, that's the length of the Fa series minus the Fourier series. Right? Life is good. Tn f of x minus Sn f of x is just the sum, and goes from minus n to n of minus n over n f hat of n e n of x. Because remember, the weighted coefficients here was, maybe it's a plus, I think. Is it minus?
It's n minus n over n.
Okay, it was n minus n. I think the coefficients here were n minus n over n f hat of n e n of x. Doesn't really matter if it's plus or minus because I'm about to square it. So it doesn't really matter. So that's what Tn of f is. Oh, big N over big N is just 1. When I subtract this, good, they cancel. And I'm left with just little n over big N. And so now, if I want to calculate its L2 norm, I integrate the square, I integrate the square. But when I integrate the square, the only thing that matters is when en hits e negative n. So I'm going to get just complete reinforcement, and so I'll get the sum, n goes from minus n to n, of n squared over n big N squared, f hat of n squared. Okay? So this is what I get for the difference between the L2 norm, between the Fa series and the Dirichlet series.
Why did we use the en term again?
Well, I'm integrating. I'm integrating from 0 to 1.
Oh, yeah.
And I have a finite sum, so I square the sum, I use the variable n, I use the variable m. The only term that matters is when n equals negative m. So all that's left is the sum. Alright, so now we have to figure out what is the sum. What do you hope the sum equals in the limit? 0. So if this sum doesn't equal 0 in the limit, we're in trouble. So let's look at this sum in different regimes. And this is again one of the reasons why I like doing this problem. I love the result. Okay, it's one of my favorite results in Fourier analysis, and so that's almost reason enough to do it. But most of you are probably not going to be using Plancherel, sadly, in your life, even though we'll have some nice applications of it. The idea to prove Plancherel, however, is really nice. Because the sum n goes from minus n to n of n squared over big N squared f hat of n absolute value squared. We want to show that this tends to 0. And again, we got here by already taking our function and replacing it by adding 0. Okay, can anybody tell me different regimes to study?
What do you mean regime?
Regimes on n. Right now I have little n ranges from minus n to n. I want you to segregate, I want you to discriminate, I want you to do everything that Williams is teaching you not to do. Group people based on their intrinsic external properties.
What if instead of like negatives to like a negative epsilon and a positive epsilon?
Well, since the n's are integers, if you just have an epsilon,
Oh, that's true.
so your epsilon has to depend on big N.
Right.
So you want to somehow discriminate. So if here's 0, here's n, here's minus n. A good idea is have some band about 0, and that's region 1. And then have everything else as region 2. Can region 1 have bounds that are independent of big N?
No.
No. I mean, it can, but it's probably not going to be useful. So the question is, how much do we want to do? We can always play the game, let's try n to the delta, and give ourselves a free parameter. I've been around the interval a few times. I'll just start off with maybe square root of big N. What's nice about this? Well, if little n is small relative to big N, little n squared over big N squared is still small. And in fact, it's going to be small even when I sum a bunch of terms. So the idea is, if little n is small, the n squared over big N squared is going to be small even when I count over all such n. And it's not really going to contribute. All right, well then what happens when little n is large? That's bad. So how do we handle little n is large?
F hat small.
Good, why is f hat small?
Because it's continuous into 0.
Right, because we know that the sum of f hat of n squared converges. So from some point onward, I can make that sum as small as I want. And all I'm doing is I'm making it even smaller by multiplying by something less than 1. So that's how we're going to finish the proof. Okay, so the first thing is, there's a really trivial bound for f hat of n. This is equal to the integral from 0 to 1 of f of x en of minus x dx, absolute value. This is less than or equal to the integral from 0 to 1. Bring the absolute value inside. Okay? So, if my function is L2, if my function is continuous, I'm fine. I have some bound for f hat of n coming just from this. Okay? However, have I told you the function is L1? Is our function L1? No, we just assumed our function is L2. Now, technically, yes, I have the assume f is continuous, so if f is continuous, then we would be okay by this. But I would like to avoid using continuity if possible. You know, can I get this bound? This bound seems to imply I need my function to be L1. If I'm continuous, that's not a problem. If I'm not continuous, this is an issue. But there's another bound I have for this. I could say, well, you know, f hat of n in absolute value is less than or equal to the square root of the sum, n goes from minus infinity to infinity, of f hat, I guess I'll use another letter, I'll use the letter m. Why is that true?
It's a whole thing. It's just a segment of the.
Yeah, I mean, just this one term here, if I just include the term m equals n and take the square root, that's this. I've just added a bunch more terms. And by Bessel's inequality, this is at most the square root of 0 to 1 f of x squared dx. So if I know my function is an L2, I can at least get that the Fourier coefficients are bounded. I can get a better bound if I know my function is an L1, but I don't need the full strength of L1. So now we just have to finish analyzing this sum. And so we're going to break it up into two cases. You know, the first case is when n is close to 0, so say within square root of big N. And in the second case will be when n is far away. Okay. So what do we get? We get the sum, absolute value of n less than or equal to the square root of n squared over n squared, f hat of n, plus the sum, absolute value of n is greater than, square root of n is less than n in absolute value, is less than or equal to big N of n squared over n squared, f hat of n squared. So when I look at this sum, how many little n's do I have? How many little n's are in this sum?
2 root n
2 root n
plus 1.
2 root n plus 1, right?
But one of them goes to 0, so does it count?
I'm sorry?
But
Right, and so when we actually take the one that equals 0, it actually is fine for us because we have the 0 there. So we're fine, so we can actually even ignore the plus 1 if we want to. So of the terms that matter, it's 2 square roots of n. Now, how do I bound little n squared? I could replace f hat of n, oops, I'm sorry. I could replace f hat of n squared with its bound, and I could do, well, let's say the sum of little n squared would be like n cubed over 3. I could try to do all that stuff. Let's be crude. What's a crude bound for each n squared? N. Because each little n is at most square root of n in absolute value, so if I square it, it's at most big N. I get to divide by n squared, and now we know that f hat of n is bounded. So I can put in at most some bound b squared. And this is from f hat is bounded. So we'll see that this term is going to go to 0 rapidly as n gets large. We have an n to the 3 halves upstairs, we have an n squared down below. So in fact, we could have actually gone further than square root of n. We could have gone up probably to about, what, 3/4? Gotta be careful.
What?
So-
3/4, right? Wouldn't it take us? Wouldn't take us
Slightly less than
like
3/4. No, I'm sorry, we can't go to 3/4. So somewhere between 1/2 and 3/4. So 3/4 would be too much. If I put in 3/4, I would have big N to the 3/4 becomes big N to the 3 halves, but then I would have N to the 3/4, that'd be N to the 2 1/4. So that'd be too much. So N to the 3/4 is too much. N to the 1/2, I still have some wiggle room. We could easily figure out exactly how far we can go. No one cares. Moving on, right? Over here, when we look at this is bounded by the tail, right? Because little n squared over n squared is bounded by the tail. So this is just bounded by the sum of big N, square root of n less than n in absolute value, less than equal to big N of f hat of n squared. But what do we know about this term? So what do we know about this term? I'm sorry, it goes to 0, because we know the sum of f hat of n squared is finite, so the tail has to go to 0. Since the sum of f hat of n squared, and it goes to minus infinity, is less than equal to the integral from 0 to 1 of f squared, the tail goes to 0. And so now all we have to do is just choose n large enough to make this less than epsilon. So choose n large, so above is less than epsilon. And that finishes the proof. Okay, so now we know Plancherel's theorem is true. So my physicists now are in the hot seat. I want you to tell me why in physics you might care about Plancherel. And so Plancherel tells us the sum of f hat of n squared, and goes from minus infinity to infinity, is the integral from 0 to 1 fx squared dx. So my physics students, tell me either the left or the right hand side, why might you care about one of these in physics? Yes?
The right hand side,
Yes.
assuming f is a complex function, is the wave function in quantum mechanics.
Excellent, right? So for those of you in mathematics, here is a really good reason.
Wait, can you clarify the reason? I didn't get it.
Yes, so the reason is the following. In quantum mechanics, we have a wave function that describes the probability distribution of our state. And if you want to find out what's the probability in a certain region, you integrate the absolute value squared of your probability wave function. It's the complex conjugate, it's the integral of the absolute value of f squared that matters, that encodes the probability. You can think of this as the probability. So what should this integral equal? So in physics, you often normalize things so that the integral is 1. Well, if my integral is finite, I can always divide f by a certain number and make the integral 1. So if I say my function has finite integral, I can often renormalize to make it 1. It turns out in a lot of things in number theory, we look at generalizations of this and we're torn. Because we would love to have the integral be 1, but when we look at associated Taylor series expansions, it's very useful to have the first coefficient 1. Typically in life, you cannot do two normalizations at the same time. You have to pick and choose. You can make the integral equal to 1, or you can make the first coefficient equal to 1, but odds are you can't have both. And for what I do, it's typically better for me to have the integral not be 1, and to have the first coefficient be 1. And maybe later, it's related to generalizations of the Riemann zeta function. I'll talk a little bit about that. Okay, do people want to hear about how to handle general L1 functions by step functions, continuous functions, or do you want to just jump to an application? Application, okay. So let's let f of x, I think I want to do x minus a half. Or is it more? I want to just make sure I do the right application. Nope. 1/2 minus the absolute value of x. For minus 1/2 less than equal to x, less than equal to 1/2. What does this function look like? It's been a long time since we've plotted something. I mean, they always tell you draw a picture. I mean, I've drawn plenty of pictures in this class, and I can prove it by going to the videotape. But I've very rarely plotted functions. Why have I plotted so few functions in this class?
Because you plotted So visualize a complex function here is going to do it? Can
Yeah.
plot them?
How many dimensions do I need?
4.
4. I'm given 2. Right? Maybe if you gave me a 3-dimensional blackboard, I'd be willing to try. But with just a 2-dimensional blackboard, that's not fair. So, sadly, it's very hard to visualize complex valued functions. Real valued functions I can visualize. 0, minus a half, 1/2. What does the function look like?
A triangle.
Triangle. Which triangle?
So,
Yep. And in fact, this would be a periodic triangle. It would just continue on and on and on. So what's nice is this is a periodic function. It's continuous. Everything is fine. So Plancherel's theorem should hold. So I can either tell you what the Fourier coefficients are, or we can actually do the calculation. Sure, let's do a calculation. You should probably compute something in your life, right? F hat of n is the integral from 0 to 1. Oh, sorry, no. Negative 1/2 to 1/2 of 1/2 minus the absolute value of x times e to the negative 2 pi I n x dx. Okay. What's the easiest value of n to do?
1. Or 0.
0. Right? When n equals 0, what do we get? This is now 1. The integral of a half and minus a half to a half is just a half. And now we have to integrate the absolute value of x. Is there a better way to find the answer when n equals 0?
Just average.
Find the average.
Yeah, find the area of the triangle. Right, when n equals 0, it's just the area of a triangle. The base is 1. The height is a half. And so when n equals 0, what do we get? I'm sorry? 1/4? I think we get 1/4. Let me make sure that this is the one I want to be doing. Okay. So now the question becomes, what do we get for other values? And so now we have to start going through the integrals. What about this 1/2? If n is not equal to 0, does the 1/2 matter? No, the 1/2 doesn't matter. Why doesn't it matter? It integrates to 0 because it's going to be 1/2 times this, which integrates to 0. Okay, so now we only have to worry about integrating negative absolute value of x. Well, if you think about it, this I can write as cosine 2 pi nx minus I sine 2 pi nx. Which one matters?
Cosine.
Cosine y.
Because it's an even function.
Because this is an even function, because it's absolute value of x. Even times odd is odd, so I don't have to worry about that. So if n does not equal 0, we get a negative. And now, because this is even, I can integrate from 0 to 1/2 and double. 2 integral from 0 to 1/2 x cosine 2 pi n x dx.
Why there? Minus.
Because I have minus the absolute value of x.
Is that still an absolute values?
No. Because it's an even function, so I can go from 0 to 1/2 and double. How do I integrate this? Integrate by parts. Oh, so much fun, right? So u equals x.
I think they're doing calculus over there. Can we make them do it?
I'm sorry?
They're doing calculus over there. Can we make them do it?
So dv is cosine 2 pi and x. B is we have to multiply by 2 pi n. Now the derivative of sine is cosine, so I don't need any minus signs, correct? And so I get negative 2.
Don't you have to divide by?
Didn't you
Is
have
that-
one
oh, did I
over
do- I'm sorry. Sorry, I have to divide by it, yes. Sorry. So now I have negative 2, and then I have the xv term. So when, for the xv, when x equals 0, I get 0. When x equals 1/2, I get the sign of pi n, which is 0. So that boundary term doesn't matter. The negative and the negative now in the integration by parts reinforce. So I get that this equals 2, and I have the integral from 0 to 1/2 of sine 2 pi nx over 2 pi n dx. What's the integral of sine? I'm sorry? Negative cosine. So I would get 2 cosine 2 pi nx. I have now a 2 pi n squared down below, and my bounds of integration have flipped. Okay. And now when I plug in 0, cosine of 0 is 1, and cosine of 2 pi n times 1/2.
It's an N.
Depends on n.
Yeah.
So I get 2. So now cosine at 0 is always going to be 1. And what can you tell me about the cosine of pi n?
1 to N.
It's negative 1 to the n plus negative 1 to the n over 2 pi n squared.
So for odd values, minus
So
0.
for odd values of n,
No,
oh wait, sorry, there should be a minus sign.
Okay, then
So now I'll let you correct because that was my
So
fault.
then for even, it's
For even values of n, it's 0.
and
for
for
odd-
odd,
Right. So the only thing I'm worried about is, did we do the initial calculation when n equals 0 correctly? Yeah, must have. So we get, so when n is odd, we're going to get a 2 over here, a 2 over here, the 2 and the 2 reinforce. And so we should get a 1 over pi squared, 1 over 2m plus 1 squared, if 2m plus 1 equals n. Okay? So if we've done all the calculations correctly, we now have the Fourier coefficients. And so now, we go back and we use Plancherel. And we would get, when n equals 0, we had 1/4. And then we have a sum over n odd. And when n is odd, we actually just double this, right? We would have a 2 over pi squared 1 over 2m plus 1 to the 4th. Pi to the 4th. And then, was it 1/4? So if it's 1/4, then when we double it, it becomes 1/16. And then on the other side, we integrate from 0 to 1 of the square of 1/2 minus the absolute value of x squared dx. So by symmetry, I'm sorry, minus 1/2 to 1/2. But by symmetry, I can go from 0 to 1/2 and double. So we've run out of time, unfortunately. But can you compute this? Yeah. And you'll have a formula for the sum of 1 over 2m plus 1 to the 4th. Now you'll only have it for the odds. So I'll talk a little bit on Friday's class about how we can get it everywhere just from knowing it from the odds. But knowing it just from the odds is more than enough. We'll bring this over. And in fact, this tells you, since this is not going to involve pi, and this doesn't involve pi, what is this going to involve? Has to be involving pi to the 4th power. Okay? Alright, so we will, finish this off on Friday.